Hello, everyone. I'm Sri Krishnan Shankaran, host of the Material Minds podcast, the place where we talk to the people exploring new materials for a better world. Today, we talk with Mohammad Torkamanzadeh, who's just finished his PhD and is a postdoc in the Energy Materials Research Department with Professor Volker Presser here at INM. He talked to us about what he does in electrochemical water desalination, so pulling salt out of water, but even more, pulling specific ions out of water with special electrodes and electrochemical cells. It's a very fascinating and enlightening conversation that we had. I hope you also learn a lot from it and enjoy it. So, with that said, here we go. Hi, Mohammed.
Hi, Shirish.
Yeah, it's great to have you on the podcast. Thanks for agreeing.
Thank you. Thanks for the invite. It's a pleasure to be here.
Yeah, absolutely. So you work on something about water desalination, pulling ions out of water and so on. So it sounds a bit like magic, and maybe even it is with today's technological advances.
Right.
But yeah, let's get to know it a little bit more. And I've asked you to prepare a description of what you're doing,
right,
with 3 levels of complexity.
Right.
The first one's the most complex, unnecessarily complex. I call it the scientific show-off, like to say that, you know everything about your science and you can say it in the most complex way that no one else can understand it,
Right.
maybe. An example of that is if you take the saying, the early bird gets the worm.
Right.
And in German, that's der frühe Vogel fängt den Wurm.
Right.
Right? But instead, this scientific show-off version could be an organism of avian nature that initiates its daily activities prior to its counterparts, possesses a significantly increased probability of securing a vermiform creature for sustenance.
Right.
Which is ridiculous,
Yeah.
right?
Yeah.
But
I'm not sure if I can do that, but yeah.
Well, I have to admit that I got help from ChatGPT for this. So
okay. You should have told me.
You can cheat how much ever you want on this. But in any case, I'm curious to hear what you have to say about your project in the most complex way you could come up with.
Sure. So if I want to describe it like that, my research focuses on the utilization of electrochemical processes, charge transfer processes, to selectively remove ions from the electrolyte interface and immobilize it, and then regenerate the electrodes by applying a reverse potential.
Woof.
Was that
that's got a whole bunch of jargon in there. Okay. Right. So I got electrochemistry in there, which means there's chemistry and there's charges buzzing around somewhere, electricity. And then I think I've forgotten most of the other words that you said.
That was my goal.
I think you succeeded really well. Can you say it once again?
So with the same level of complexity.
Just the same
thing.
So
we use electrochemical processes, we use charge transfer materials to selectively pull ions from water into the electrolyte interface so that we can immobilize it there, and then we give it back to the water, then we regenerate the electrode, and that's one cycle.
Okay, that's one cycle. That sounds like a lot is happening at once. It's starting to make a bit more sense, I think, in my head. It is an electrochemical process. You're pulling ions out of water. What those ions are, that's, I think, a curiosity that we'd have to get into a little bit. You have electrodes involved in the process. And then you said there's a recharging happening and then something going back into the water or so. And the more the more I start thinking it, the more vague it's getting in my head, right? Like to understand. But okay, these are all the elements that I could pull out of what you're talking about. And I know that you're working with a bit of water desalination.
Yes.
So the ions I would associate with salts in the water to some extent. but yeah, that is kind of the limit that I can that I would be reaching with this level of complexity of
Yes.
the description.
Yeah. Yeah.
So with that, maybe it's worth it to go to the next level,
Yes.
level which I'd like to call it the scientific expert, which means you are talking to your colleagues,
Right.
you know,
Right.
other people in your group, maybe your boss, maybe someone at the conference,
Mhm.
and then you're basically just discussing your work with
Yes.
them.
Yeah.
So yeah, can you describe it in that way?
Sure. Yeah, so then I would say we have an electrochemical system, just like a battery, but the difference there is that in a battery, for example, in our phone, in our laptop, the electrolyte, so the battery is closed, nothing moves there. But what if we had this battery with flowing electrolyte? Now, water, so salty water comes in, and you apply a certain voltage, like 1.2 volt, and the positive and negative ions go to the electrodes, stay there. And what comes out of the cell, this electrochemical cell, is partly desalinated water.
Okay.
And then in the next half cycle, you apply a reverse voltage or you short circuit the cell, and the ions that were once in the electrodes get ejected back into the water. And there you have got your next half cycle, and you get ready for the next cycle. So you regenerate the cell. So this is called
Okay.
electrochemical desalination, very simply put. But you can get it to the next level, and just for the so extend it from just from sodium chloride, which is the table salt, and go to, for example, multiple ions. So lithium,
Okay.
calcium, sodium, and magnesium, calcium, and then selectively just go for lithium.
Okay. Selectively go for
Yeah.
for one of the ions.
Right, exactly.
Okay. That's getting yeah, much more understandable and very interesting.
Okay.
So first you said passing an electrolyte
Right.
through your
Yeah.
system, and what I understand is electrolyte is basically a liquid
That's
of any
right.
sort that
Yeah.
can conduct
Water-based,
to
yes.
some
Yeah.
extent. Yeah. And so in your case, it's water which has these ions or the salts which have ions in them, or which
Right.
are made up of ions.
Right,
Basically. Yeah.
right, yeah.
And then your electrodes are able to pull these out.
Yes.
And then you have another cycle where the electrodes are basically able to spit them back into the water.
Exactly.
This is where I'm a little bit lost. Why do you need to take them out and then put them back in the water?
Right, right. So you cannot infinitely remove ions from the aqueous media, from the water. There has to be a reversibility. So the electrode has a certain capacity, and so that it reaches the saturation after a while. And so, for example, we're going to go through these materials as well.
Okay.
For example, carbon is one very typical electrode.
Uh-huh.
It has a limited capacity. So, for example, for each 1 gram of carbon, you can get out something like 10 to 20 milligram of sodium chloride.
Okay. Uh-huh.
Yeah, so we've got electrodes that can take up much more than that. But
Yeah.
let's take carbon
Yeah, okay.
for the moment. So this 10, 20 milligram of salt that you took up, you have to get it out. So, for example, you've got this for reverse osmosis, maybe
Yeah.
you're familiar with. So the salty water has to go somewhere.
Yeah.
So you cannot just desalinate water forever.
Yeah.
So this is this system's way of regenerating it. So you
Okay.
apply a potential, you get the ions into the electrode, and then you apply a reverse potential or short circuit it, and then you give it back to the water. That's the part of the water that you have to discard.
Yeah, okay. So, but then is the amount of water from which you're pulling out the ions
Right.
much larger in volume compared to the amount that you're putting it back into?
Exactly. So that's the concept that we call water recovery ratio, for example.
Ah, okay.
So yeah, the water recovery ratio could be 50%. So you put in 1 liter into the system, you've got half a liter desalinated, half a liter salty.
Okay.
But you can also play with that ratio.
Uh-huh.
So you can go, for example, to 80% water
Okay.
recovery and 20%. But that also changes the energy consumption.
Ah, okay.
And, yeah, other factors as well.
Okay.
Yeah.
Interesting. But by doing these cycles, you can keep on passing new proportions of water through your system, and desalinating a certain amount of the water that you see.
Right.
Yeah.
Right.
Okay.
Exactly. Again, desalination is one particular application of it.
Uh-huh.
But as years went on, this research community went from mere desalination now to niche applications like lithium selectivity.
Yeah, so that's
for
what I
pollutant
wanted to get to
removal.
next.
Yeah,
That you
yeah.
talked about the selectivity. So why lithium? What is so interesting about lithium that you want to take that
Sure.
out? Or maybe you're taking out other ions, but this is the
Sure.
one you mentioned.
Yeah, yeah. Shall I explain it now, or shall we go to the third level of
Oh yeah, so
complexity?
if you think it makes sense with the third level, then yeah, absolutely, let's do that.
Yeah,
Let's
sure.
go to third level. Third level is what I like to call the science communicator,
Right.
and it's more that it's a bit like you have a relative, a nice uncle or aunt or grandma or
Right.
nephew or niece, whatever
But,
you
but
like.
the grandma is also a material scientist.
Oh yeah, so this is why I
No,
say
just kidding. Just kidding.
yeah, that's why I actually did expand the
Yeah, no.
category into uncle or aunt. Basically, it's
Yeah.
some relative that's clueless about what you're
Yeah,
doing,
sure, sure.
but who's very curious.
Right, right.
And you're all the way here from your hometown, you
Right.
know, in Saarbrücken in Germany, doing something in an amazing group in the Material Science Institute. You're working with water is what
Yes.
they know, but not much more.
Right.
So what would you tell them
Yeah, sure.
about what you're doing?
Yeah, yeah, yeah. That's a great approach by the Bashir.
Mm-hmm.
So I think Einstein once said that if you can't explain it simply in a simple way, then you yourself don't know it well.
Mm-hmm. Yeah,
So
in
that was a
principle,
great
yeah.
approach. I loved it. Thanks.
Yeah, great.
Yeah. So my grandfather once asked me, by the way,
Okay.
hey Mohammed, what is this thing that you're busy with?
Yeah.
And so I try to say, so you see this water so you see this ocean water that's salty. We try to get the salt out. So I left it there.
Uh-huh.
And I said, we do also chemistry. And so I was trying to see if he catches some part from
Yeah.
from this soup. And he said, so he's also in the retail of animal food and also chemical fertilizer, these kind of
Okay.
things.
Uh-huh.
He immediately related it to his work. So he's
Yeah, okay.
when I said chemistry, he said, "Oh, like what we have in chemical fertilizer."
Yeah, okay.
And
Uh-huh.
I said, "Yeah, pretty much along those ways."
Uh-huh.
Yeah, but yeah, to a very lay person, I would say getting water treated. So getting dirty water cleaned, or so depending on the level that's
Yeah.
of the person. So getting the salt out, getting the pollutants out, these kind of things.
Okay, so where do you fit in the lithium aspect into that? Is that a pollutant? Why do you want to take that alone out, or is it useful for something else?
Yeah. So lithium is becoming more and more relevant.
Uh-huh.
So with this, with the electric vehicles market expanding rapidly, also the electronics that we have in our pockets, so phone, laptops, this camera, etc.
Yeah.
These are mostly lithium-ion batteries.
Okay.
And you have to think about when these end of life appliances, so when the phone dies at the end after 2, 3, 5 years, what do we do with these devices? Now, lithium in those batteries are valuable. And so, for example, Europe is not a major lithium-producing continent.
Yeah.
So most of the lithium comes from South America, like Bolivia, Argentina, Chile, and also from Australia and China. So these are limited. So these are the dependencies that Europe has to those countries. So apart from the geopolitical implications that has, there's also the transportation footprint.
Yeah.
So just imagine millions of tons of lithium getting on the ship from those countries and coming to here.
Yeah.
Now, one way to address that is to reuse these devices that we have when they reach their end of life. And so one way that people do it is that they get the phone, put it into the shredder,
Okay.
and then at the end you've got a black matter, and then you leach that black matter with a potent acid like HCl.
Okay.
And what you've got, so this is a hydrometallurgical approach. what you've got is a soup with not only lithium but also so many other species in there. Now the key is, can we selectively get lithium out from that mixture? So that's one of the main focuses of our group.
Okay, so it's not necessarily seawater. We're talking about water that's coming out of this process.
As well.
Okay.
Yeah. So from seawater, for example, has so ocean water has more than 200 billion tons of lithium. So meaning
wow,
unlimited
okay.
source of lithium. But the problem is that the concentration of lithium there is very low. So it's around 0.1 to 0.2 ppm. Now
Parts per million.
Exactly.
Yeah.
Parts per
okay.
million. Yeah. And the total salinity of the ocean water is 35,000 ppm, mostly NaCl.
Okay.
So just very much 35,000 of ppm of salt, just 0.1 ppm of lithium.
Oh wow. Okay.
Now, if someone can have a system that sustainably and also in a very scalable manner can get the lithium out of seawater, that's a real game changer.
Yeah.
But we're not there yet. What people usually do, what we have companies doing right now, is to get these, this recycling of used lithium-ion batteries, or utilizing geothermal water, so geothermal wells, and there's also those in Germany as well. So which has a much higher lithium content already to begin with.
Okay, but it's still a good source to get a good amount of lithium.
Exactly.
For usage.
Yeah. So for example, Germany, we're right now sitting on a one of the largest lithium reserves in the form of geothermal wells.
Oh wow.
Yeah.
Okay.
So there's this Upper Rhine Valley region in Germany. Just consider this triangle from drawn between Frankfurt, Stuttgart, Saarbrücken.
Okay.
So around this area. There is this above 3 million tons of lithium.
Okay.
In the form of geothermal water. And there's a company actually doing that. They get the lithium out. So they get the warm water out of the earth, kilometers deep.
Yeah.
And they selectively get the lithium out. They also get the heat out. They also get the electricity from it.
Okay. Wow. That's amazing. So you brought some stuff here. Is this is this the kind of the electrochemical cell that you use?
Exactly.
So what Mohammad has is, can you describe it? It's like a transparent block with many kind of valves sticking out of it.
Right.
Screw valves, I guess, that you can screw on and off.
Exactly.
And then it looks like it's made of like 2 or 3 parts put together.
Yes.
With some flat black stuff inside it, right? Like, or sheets inside it.
Yes.
Right?
So that black stuff that you said is graphite. So remember, we talked about electrodes and water passing. So this is a type of that system. So water, for example, so salty water. So just think about water with sodium chloride, so NaNCl.
Yeah.
And so water goes in from here, comes out from here, and so these are graphite sheets inside the cell, and you've got this electrode plug. So you put the electric wire here, one here, and then graphite is your current collector. You've got your active material as electrode there, and you apply, for example, 1.2 volt, and so the water goes in with the ions passing, and you apply the voltage. The ions go to the negative and positive electrodes, stay there, and so the water that comes out from this side is partially desalinated.
Yeah.
Yes.
Okay.
Yeah.
Okay.
And in the next half cycle, you short circuit it.
Yeah.
And then you have a salty brine coming.
Yeah.
out.
Okay.
You discard that one, for example.
Okay. So, and graphite is basically carbon. Then.
So graphite in this case is, yes, it's a carbon, but we use that as a current collector. So the graphite itself doesn't have any effect on the performance of the system.
Okay.
So it just reaches, it just makes the electronic charge to reach the electrode.
Okay.
That's the effect that it has.
Okay.
So a cell that has only graphite won't perform
Okay, won't
at
do
all.
any of this.
Yeah,
Okay,
yeah, yeah.
okay, interesting.
So electrode is where the magic happens.
So what is the electrode that you have in there?
Yes. So we use various various types of electrodes in our group, and we try to develop them ourselves. We also go with the available ones commercially. We modify them, all sorts of things. But so carbon that I referred to previously. So this is a 3D printed. Maybe you want to take a look.
Yeah.
Yeah.
Well, it's for those listening, it's a 3D printed cube,
Yeah.
but which is made up of twisty surfaces all throughout. I don't know how to describe it actually. It's very twisty surfaces, large surface area overall. If you opened it
Exactly.
up, I guess, which might be the point.
Yeah. So we wanted
yeah.
to show here the system of pores within a pores within pores. So a hierarchical system. You see here you've got these big pores, and then inside those there's pores, and that's where the ions can get accommodated.
Okay.
And so that can serve as electrode. And so this highly porous material, around 1,000 to 2,000 square meter per gram of it.
What? Sorry, what did you say?
1,000 to 2,000 square meter per gram.
Per gram.
Per
So
gram
1,000 to 2,000. So if you basically unwrap it
Yeah.
and lay it out flat, it's 1,000 to 2,000
Yeah.
square meters.
Yeah, just 1
per
gram of
gram.
it.
Wow.
Yeah.
Okay.
Maybe the area of the soccer pitch.
Yeah.
Something
Yeah.
like that.
In
Yeah.
1 gram, that is
Yeah.
incredible. Yeah.
And then there's this material, for example, Prussian blue or Prussian blue analog, in German Berliner Blau. So this is so this has been used for centuries now, mostly as pigments. So, for example, in inks of the pens that we have, if they're black or bluish, there's this in them. But there can also be usage for electrochemistry, also for biomedicine, etc. And so you've got this. So the chemical formula is iron ferrocyanide. So irons at the edges, at the vertices, and carbon and nitrogen in the middle. So irons here, and carbon, nitrogen in the middle. And a part of the ions could be exchanged with other transition metals like copper or nickel. Then it is called Prussian blue analog. PBA.
Yeah. Okay.
Yeah. So we talked about carbon. That's around 10 to 20 milligram of salt adsorbed per gram of it. With these, you can go above 100 milligram.
Oh,
So
okay.
they have got higher capacity.
Nice. Yeah.
Yeah.
Okay.
And so both of these materials, either carbon or Prussian blue, are used not only in water systems, electrochemical desalination, but also as electrodes for batteries. So batteries. So this is lithium-ion battery, rechargeable as well. So it might not be visible with the camera, but there's a USB plug here.
Yeah, I think in the other one also there is one, right?
Yeah,
like in the front.
Yep.
So yeah, what we have in our hands are just regular AA batteries, and also a button battery.
Yes,
And in the
coin
AA
cell.
battery,
Yep. Yeah, we call that coin cell or button
coin cell or a
indeed.
button battery. Yeah, and in the AA battery there is a USB input plug, a port. Because it's a rechargeable battery.
Exactly.
Is this something made here, or is this by a company? What is?
This is made by a company. This coin cell we make here ourselves.
Okay.
And so we get an electrode, or we make an electrode in the lab with the furnaces that we have, with other synthesis methods, and then we take it and use it either in a coin cell or a custom-made cell that we have in our lab, or in an electrochemical cell.
Okay.
So so in our group, Energy and Materials Research Department at INM, Professor Presser is the leader there, and we're around 24 people at the moment. And so we are two tiny. There are two fractions there. So one is water subgroup, and one is energy subgroup.
Okay.
And so in the water subgroup, we are around 7 or 8 people, and so that's the kind of things that we work on. And then the rest are energy, battery, supercapacitor, energy storage.
Okay, and you
those
use
work with.
the similar kind of electrodes for both, just repurpose them to be adapted to
That
each
happens a lot.
method.
That happens
Yeah,
a lot.
that
Yeah.
happens
So there's a lot
okay.
of overlap between
Okay.
us. Yeah.
Yeah.
A lot of things that is used in one of the subgroup could be used in the other as well.
That's really fascinating. Wonderful.
Yeah.
That's an excellent use of everything that you're generating scientifically out of it. So you just finished your PhD,
That's right.
is my understanding. You
Yeah.
defended last month very successfully, and the work that you've been doing is just fascinating. What does your future look like? Where do you think you're going to go with all of this?
Yeah, right. So just last month I defended it. So the thesis, by the way, is available online. Just Google my name plus the thesis. So the next for me, so there was a versatile types of activities that I've been involved with here. So getting the new students up to speed. So how things work around here, how the cell works, how to make a cell, analyze data, and at the end publish it. Or I've also worked with industry projects, so 2 projects, water softening. So getting, for example, magnesium and calcium out of the water. And I've also been involved with teaching, so teaching thermodynamics to undergraduate students. And also I help with writing research proposals to get funding from funding agencies. So in the future, I'd love to have a job that combines these skills that I gathered through all these years. Could be a research and development area in industry. So I'd love to see the research that I've been involved with in these years translated into something tangible, into something applicable in industry.
Okay, so
Yes,
you
but
are.
I'm not sure where the future takes me.
Yeah. Okay.
I'm
yeah.
excited.
It's an exciting transition moment in your life, and it's interesting to hear. We do a lot of application-oriented work at INM, and it's interesting to hear as you do more and more of that kind of work, how you get motivated to want to see it applied really.
Exactly.
And yeah, so it's very understandable that you'd want to look for being able to use your expertise in industry and actually get it to the people and out in the environment to help make a better world in the end.
True.
So it was wonderful talking with you.
Thank you, Shirish.
Mohammad. This is very enlightening, everything that you explained and all the things that you brought with you, especially since the start of the conversation with the very complex explanation of what you did. Now I think I understand basically everything that you described very clearly.
Thank you. Thanks for the invite. It was a pleasure to be here.
Yeah, absolutely. And good luck with the future.
Thanks.
So thank you everyone for listening and watching. We were talking with Mohammad and his exciting work on water desalination, the electrochemical processes he uses, the electrodes he uses, the electrochemical cell he uses. It was the time just flew talking with Mohammad, and I just learned so much. I hope you did too. Our podcast episodes are up on YouTube. You can listen to them also on Spotify. We also put out clips of them on our Leibniz INM accounts on Twitter or X, on LinkedIn and Instagram. So you can catch us in many places. And until the next episode, see you everyone.